Hi, in this video, we're going to take a look at what do we do when we're doing a least squares regression model, so a standard regression model, but when we look at the diagnostics of our model, it looks like our residuals are not independent, identically distributed. I know that this is a burning question in your minds, right? Everybody asks me, like, what do I do if it's not independent, identically distributed residuals? I'm walking down the street, people randomly ask me this all the time. All right, so consider, just think about the situation of like multiple linear regression. Standard linear regression, least sum of squares is how we're defining the line of best fit. All right, and so something that is a critical, super critical assumption about this is that we have independent, identically distributed, or not identically distributed, independent constant variance on our residuals. All right, and typically we're going to say normally distributed, so it will be independent, identically distributed. Now, let's say that I ran my model and I'm feeling good about the coefficients. I'm feeling good about the fitted values. I feel good about that aspect. When I look at my residuals, they don't look to be independent, or they don't look like they have constant variance. Now, constant variance that could be resolved with a transformation, such as a Box-Cox transformation, specifically the log transform, but maybe that transform isn't enough. Okay, or the independence example or situation comes up, and so what we're going to do? All right, so we're going to take some text from time series analysis and its applications, chapter 3, section 8. Here is the name of the authors. Here's their GitHub page. And UCF students can download the textbook for free through the library. All right, so let's dig into this. All right, so let's say I'm in the situation where I can't accept the independence constant variance assumption of the line of best fit. Okay, so what can I do? Well, what I'm going to propose to you is that we're going to kick off an ARIMA model on our residuals, and we're going to incorporate that into our modeling, and then this hopefully will resolve all of our issues. Okay, so here are the steps that we're going to go through. First and foremost, I'm just going to go ahead and fit a regular old line of best fit regression model, and I check my diagnostics, and then I'm in the situation my residuals don't satisfy the assumptions. Okay, so now what I'm going to do after that, I'm going to take the residuals from that model that I've already rejected, and I'm going to fit, and I'm going to identify an ARIMA model on that. Now, when the textbook says identify, that means identify P and Q on the model. All right, so here we're going to be using the autocorrelation function plot and the partial autocorrelation function plot to identify a suitable degree. We could also use the we could also use like auto.arima in the forecast package to do this for us. Then once I've established what model I want for the ARIMA, then I'm going to go ahead and fit the autoregressive moving average model of degree PQ. Notice that it's not ARIMA. We're not doing differencing. Then I'm going to go and I'm going to check the model that I get. I'm going to check to see, do my new residuals, after I refit my model, does it look like we have like white noise on our residuals? And I might tinker, I might adjust things. Maybe a good time to adjust the covariates if need be. Like we're always in a continuous process of trying to improve our model. And then if I feel good about it, I'll actually go through and use the ARIMA model to get the result. And now these two steps are going to be so all of this will be spit out in one shot using the ASTSA package in R. The seasonal ARIMA function will do it for us immediately. All right, so let's consider correlated errors in our linear regression model. And so in fact, The results that we're going to get is include non-constant variance also, but here we're just going to focus argumentatively on correlated errors. Now, here's my standard regression model, but I'm writing it a little bit different than I usually do. So here I've got y. Here I've got my coefficients. Here are the predictor variables. Notice that the predictor variables here in this textbook are z, and then my residuals are the x. So here we're treating the residuals as the time series that we're interested in. All right, so x is a time series process with a covariance function. Now, something that's important is notice that this autocovariance potentially could depend on time at this point. All right, so if I have everything the way I would want it and wouldn't even be worrying about the content in this video, the standard assumption is that our x sub t is Gaussian white noise. And so in that situation, whenever s and t are different, the residuals are independent and they have zero covariance. When s and t are equal to each other, we have that constant variance aspect. Notice that there's no s, no t in this. All right, so now when x sub t is not Gaussian white noise, something that we could do to try and recover the situation is to use a weighted least squares to get the needed assumption. All right, so what we're going to do, we're going to work this through using matrix equations. If you're not comfortable with matrix equations, trust me, this is the easy way to do it. It's a lot harder to try and slug through this using a whole bunch of linear equations. All right, so y is a vector is equal to our predictor variable matrix z times the coefficients plus our random aspect x. All right, so here y is a vector, x is a vector, beta are the coefficients. So beta is a vector of coefficients. Z is our predictor variable matrix. And so now here we have rows because we're setting this up to be time. And so normally when you talk about regression, you have your predictor variables at each individual field. Because we're in a time series lane, we're writing it slightly different here. It doesn't really make a difference for our purpose. It's Z. And what we're going to do, we're going to say that the gamma matrix is the covariance matrix for our x. Okay. Now, something to realize is that a covariance matrix, because it is, as long as the order of the values doesn't matter, then our covariance matrix is going to be symmetric. If it's symmetric, then it has a square root. And we'll go ahead and assume that we have an inverse on our square root. Now, we can weaken the assumption a little bit, but basically, for this to work out, we just need that gamma to have an inverse and a square root at the same time. All right, so y is equal to this equation. I'm going to multiply the whole equation by the inverse of the square root of gamma. All right, so let's do that. So I'm doing a little bit of multiplication, nice and easy peasy, lemon squeezy. All right, so now I'm going to make this new equation just to make this a little bit simpler. All right, so remember, gamma is a constant from the gamma matrix is a constant from our point of view. And so this new y is equal to inverse of square root gamma times y. Our new z is inverse of square root of gamma times z. And this delta is, well, you guessed it, inverse square root gamma times x. All right, so delta is a covariance matrix. And it's going to work out that if we go through, if we take the covariance, sorry, I misspoke a moment ago. If we take the covariance of delta, all right, well, I'm going to use a standard matrix covariance equation. All right, so I have a constant times the random part, and I'm taking the variance. All right, so it's matrix times vector. I'm taking the variance of a vector, so it's going to be a covariance matrix. And this is a constant matrix multiplier. All right, so how this works out is that this is similar to a constant squared, but instead of squaring, we put one part in front, one part in the back. And so we put what we have here in front, and we put its transpose behind, like that. We split that up. That's a standard matrix equation. And you'll notice I have the variance of x in the middle. Well, the variance of x is gamma, and so it works out, boom, that this is equal to the identity. All right, so now this is nice because this sets it up that my randomness isn't just constant variance and zero covariance between between values. I actually have the full-blown identity matrix instead. It's even better. Instead of being constant diagonal, it's a constant diagonal with 1. This is cool. Now, for this equation to work out, as long as gamma is symmetric, this will work out perfectly. All right, so now I've changed the equation. All right, well, let's look at the weighted estimates of the coefficients. All right, well, when I go through, I'm going to just go through, do the standard coefficient estimation here. This is the standard formula. It looks different because I'm using X star. Sorry, Z star. It's Z star. I'm so used to saying X. I've got Z star and I've got Y star in here working out. But then I replace Z star with inverse square root gamma times Z. All right, and you'll notice that things just absolutely start cleaning up nicely when I do that. And so we get this far. And so we can see that this is in fact because of the grouping together of the inverse square root gammas in here come together into one inverse gamma. This is in fact the standard weighted formula that we would want. All right, and so now if I'm going to take the variance of our coefficient estimates, I'm going to basically do the same trick I did before, where when I have a constant out front, so in this part here, only y has any variability in it. Everything else, everything I've got highlighted right now is a constant. And so with that variance vector times a matrix formula, I pull the constant matrix out front, I pull its transpose in the back. And so then here I get all of this here, boom. And you'll notice I've got the variance of y right there, which we've already established. It's going to be gamma. And then a lot of things cancel out. And so if I go through here, we have some cancellation. After that cancels, this is the same. This is going to cancel with that. Whoops. And so, oh, it's not even on the screen. It's such a long equation. But boom, we get the standard weighted least squares variance of the coefficients. So now, I've got my coefficient estimate is the standard weighted least squares estimate, and the variance of that is the standard variance of coefficients using weighted least squares. All right, so everything has worked out really nicely so far. Now, if the residuals are white noise, then that covariance matrix, gamma, it's just going to be equal to a constant value times the identity matrix. And if you go through and you plug this in, you're going to see everything collapse down, and it's going to become the standard formulas. All right, so now that sets up some good stuff, but we haven't actually involved any autoregressive moving average. Okay, so what we want to do is we'll go ahead and say that we have, let's take a look at the situation where we have an autoregressive degree P model. All right, so let's say that we have autoregressive degree P model on our errors and no moving average portion. And we're going to say that the auto covariance does not depend on time because we just took care of that a moment ago, using the weighted trick. All right, so now in this situation, phi of the backshift operator times our error time series is equal to white noise under the setup that we just built up. And so here is our backshift operator polynomial. All right, so what we're going to do, I'm going to multiply both sides of our equation by the backshift operator. All right, so here's our standard regression formula. Multiply everything in the equation by the backshift operator polynomial. Here I went ahead and brought it in, right inside the summation, that is. And then we'll go ahead and modify some things. And we're here, my y star is equal to this operator on our time series. Z is the operator times our z. And here, using the standard formula for autoregression, we know that this is going to be white noise. All right, so the standard autoregressive formula here comes into play here. Right now, I'm at Skydive to Land. The weather's crap, so I'm on the ground. There is a ground school right outside the door, and it sounds like it's pretty exciting discussion between the accelerated free fall instructor and the students. They sound pumped up. I don't know if you can hear it. All right, so here we're saying that, of course, y sub t star is our dependent variable, and our z star, which is our covariates acted on by the polynomial backshift operator, are the independent variables. And so now, just to make this a little bit more concrete, let's consider just an AR1 process. If it's just AR1, then that y star is just y minus phi times the previous y. Z is z times the previous z. And notice that we have the same j every single time, because this is for each individual covariate. Each subscript j corresponds to a predictor variable that we are using. All right, so now if we sat down and we crunched it out and we worked out the details, our autoregressive degree p sum of squares error would be this beautiful thing here. So of course, we're going to have our white noise, or our error term squared, added up. That is our sum of squares error. And if I just sit down and plug everything in as I defined above, I'm going to have each of these inside a square. Then I'm going to add them up. And then I'm going to define the phi coefficients and the linear regression coefficients as the values that minimize my sum of squares. Now, we are going to have to use numerical techniques to compute this. We can't use linear regression solutions. This is a nonlinear problem. All right, so now, what if we want to incorporate moving average into here? All right, so our trick there is that we're going to use the series representation of our white noise. And then I'm just going to plug it in, and everything's going to clean up nicely for us. And so if we want to step it up a notch, I want more than autoregressive, I want autoregressive moving average. Then what we're going to do, we're going to convert our white noise time series to purely autoregressive. And so here, my white noise is going to be replaced by a series on the autoregressive. So each individual white noise corresponds to an entire series on the autoregressive portion of the model. And we have the autoregressive part of the model is equal to the moving average part of the model. All right, and so my series coefficients on, in terms of the backshift operator is going to be equal to the inverse of the moving average backshift polynomial times the autoregressive polynomial. And so very naturally, we're going to end up getting our sum of squares error is going to look a lot like what we just looked at a moment ago. I'm going to take my residuals squared, add them up, and if I literally just drop in what we just worked out a moment ago, I'm going to have the series part times my y minus coefficients times that series applied to z. Okay, and then once again, I'm going to find the coefficients. So I'm going to find the autoregressive coefficients. I'm going to find the moving average coefficients, and the linear regression coefficients are going to be the values that minimize the sum of squares very naturally. once again, we are going to have to use a numerical technique. This is going to be more complicated than using like linear regression or something to work out. It's not too bad, but it's worth talking about in another time. All right, so what is the process? First and foremost, so I said this at the beginning of the video, but really this is the punchline of the entire video is right here. The steps to fitting a regression model with ARIMA residuals is first and foremost, I fit an ordinary regression model and I see, hey, my assumptions of independence, constant variance do not hold, okay? So then I'm going to identify the degree of my autoregressive moving average on the residuals. I'll fit the autoregressive moving average model on the residuals. I'll inspect, is that a good model for this purpose? Does it look like I have white noise residuals on this? And then I'll go ahead and update the regression model to be a better fit. So now a lot of this gets done pretty quick for us if we use the ARIMA function in the ASTSA package. And so let's go ahead and do that. Let's take the mortality, temperature, and pollution data set that we have from the package, and let's work with it. So we're going to fit a linear regression model. So I have a constant, I have a time component, I have a mean adjusted temperature squared, and then I have a particle level. All right, so each of these independently look like a covariate we would want to use, and then we have residuals. All right, and so if we were just to fit the model just straight out, we'd probably be like, you know what, I don't feel really great about the assumptions. Let's go ahead and pull in the autoregressive moving average aspect. All right, so I'm going to load my data. I'm going to pull out the time component from the time series. I'm going to mean adjust the temperature. I'm going to set up the temperature squared. Now, I could have let R do that automatically, but I chose to do it manually because that's what the authors did. What I could have done instead of doing this step, I could have actually put an exponent of 2 right there. Now, here's the summary. So the coefficients are looking like statistically significant. That looks good. But when I take a look at the residuals, I notice that I have, it's at after degree 2, the partial autocorrelation function cuts off. That's an indication that I want an autoregressive degree 2 model. And notice that the autocorrelation function trails off. All right, so what I want to do, I want to fit a degree 2 autoregressive model on the residuals. So what I'm going to do, I'm just let the seasonal ARIMA function do all the work for me. We specify PD and Q for an autoregressive integrated moving average model. And it's very nice that I just drop in my data frame. So here, this is the data frame for, now in here, I have to only have the predictor variables. Here I have the target variables. And here I specify the degree of the time series model on the residuals. And then boom, it takes care of the rest for me. So we're going through, computing it. And now I look at the residuals. Okay, I don't really see too much of a pattern. I'm not seeing any autocorrelation aspects. The residuals are within the QQ norm plot. This is looking good. I see that I've got pretty big p-values. Now over here there's a little bit, but realize I've got almost 20 hypotheses I'm testing on this. Something's gonna get low on there. So I'm feeling like I don't have to worry about the global autocorrelation aspect. Here is my outputs. All right, so now let's take a look at, let's look at AIC and log likelihood. So log likelihood is negative 1550. What was the original? Just so we can satisfy my curiosity. It's not part of the output. I was hoping it would be. All right, but we can just look and see. Yeah, I can compute it manually, but if I really want to. Unfortunately, there's no overlap in the diagnostics like this. I mean, there is over here, but all right, so here we notice that temperature has a larger p-value, but temp squared does not. So I'm feeling like we should leave it as is. We should keep that in there. All right, so now another example is to use the recruitment SOI fish data set. Once again, I'm using fish data. Somehow in my entire career, fish data keeps on coming up. I don't know why, but here we're using 6 months lag data on SOI. Here's dummy variable on SOI being positive or negative. Here's the interaction aspect, and here's the recruitment. And so we basically play the same game. I load my data, create the dummy variable. Now, this could be done with a little bit cleaner code using asymmetric SOI greater than 0, greater than or equal to, but whatever. Here, we're just making sure that our time series values, the times intersect, so it makes sense to be modeling. Here, I'm doing my linear regression model that I feel like is a good model. Notice that with the star, this gives me the linear terms and interaction. If I would have just done colon, then I would have only gotten the interaction term. I would have not gotten the linear term. All right, so here, looking at this, interaction term looks like we want to keep it. Lag on SOI looks like we want to keep it. And so here we might want to consider losing it, but it's part of an interaction term we want to keep. So we'll keep that in there. Let's plot the residuals. Okay. All right, and once again, we see that the partial autocorrelation cuts off after 2. And so we would want to use an autoregressive degree 2 model off of this. Also, the autocorrelation function trails off. And so, we can go ahead and fit exactly like we did before. Now here, I notice that the residuals are a little bit above and below the QQ norm. So I'm looking at, it might not be quite normal, but the tails are probably off. But it looks symmetric. I'm okay with that. A little bit poking out over here. So honestly, I would probably go back and just try a few other models, see if I can improve it. This is not horribly off, so I would run with it. The author of the textbook says that this could be improved with the seasonality aspect. We haven't talked about seasonality, so I'm not pulling it into here, but we'll leave it as is. This is still, I feel like, a worthwhile model to launch if we did not have the option of seasonality. Here we do have, the lung box statistic is statistically significant, but we're running so many hypotheses tests that something's going to pop below statistical significant. I'm not worried about that too much. That probably would be cleaned up if we put in the seasonal on its own. And so now we see that the autoregressive portion is statistically significant. So we're going to keep that. Now, something I want to point out, and this is not in the textbook, is that it's not, from a mathematician theoretical point of view, it's not a trivial aspect for there to be that whole square root property of a matrix. So if I have a symmetric matrix, there will always be a square root. Now, we might have to invoke imaginary eigenvalues, but if it is a symmetric matrix, actually with symmetrics it has to be real, but if it's normal, if it is normal matrix, it will always have a square root. All right, so here, this matrix does not have a square root. No matter what you try, how hard you try, you'll never be able to get a matrix that if you square it, it will be equal to this 0, 1, 0, 0 matrix. How to show that is let's pretend that there is. Okay, if there is, then this matrix is equal to this matrix squared, which is equal to this matrix. Now, if I look at this, I realize that I have to satisfy all four of these equations. Now, so that means, so right here off of this, either C is equal to 0 or A and D are equal to each other but negative sign. If C is equal to 0, well, if C is equal to 0, then when I look up here, this equation tells me that D has to equal to 0 and A has to equal 0 because of this one. All right. And so then A, C, and D are equal to 0. And so that's 0 times B is equal to 1. That can't work out. Doesn't work out. No, not possible. Now, if A and D are equal to each other but negatives, then when I look here, that's equal to 0. And then the multiplication can equal 1. Therefore, this matrix does not have a square root. All right, well, that's all I've got for you. Life is short. Do math.